Assalamu alaikum everyone. So we have been studying chapter number 8, which is mainly about the pressure drop calculation in the pipelines and the head drop and the head loss in the pipelines. So what we have studied in the previous lecture, that we can use certain equations to calculate the head loss in the pipeline. We can calculate the head loss using the journal energy equation, and we have seen two or three more equations to calculate the head loss. Okay, so this head loss equation that we studied last time, which was a function of friction factor, length, diameter, velocity scale, and the gravitational force. So this head loss can be calculated for the pipelines due to the friction in that pipeline. And this head loss that we calculate by using this equation, it is the major head loss in the piping system that only depends on the friction in the pipeline. But what we have seen in the industry is that the pipelines are also connected with other pipelines, or there could be some kind of pipe inlet system, pipe outlet system. There could be some sudden expansion or contraction of the fluid going on within the pipelines. The pipelines are connected by using the bands, joints. There are some branches in the pipelines, and there may be some installation of the valves. So due to the installation of any of these equipments on the pipeline or the devices on the pipeline, there could be an additional head loss in the piping system. So that head loss is called as the minor head loss. The equation to calculate that minor head loss, it is equal to HL, that is equal to KL, which is the loss coefficient, multiplied by velocity scale divided by 2g, and we can rearrange this equation in the form of loss coefficient, which can become a function of head loss divided by velocity and the gravitational force. So for each of the system that we see here, for the pipe inlet, outlet, sudden expansion, contraction, bands, branches, there is a specific value for the loss coefficient. So we need to calculate, or we need to see certain charts to get the value for these loss coefficients that we can incorporate in our equations to get the total value for the head loss. Now once we have the value for the major head loss in the system and the value for the minor head loss in the system, we can actually calculate the total head loss in the system. So the total head loss in the system will be equal to head loss in the major pipings plus the head loss due to the minor components on the pipelines. So for the major head loss, we will be using this equation that we studied in the previous lecture, and for the minor head loss, we will be using this equation, KL V squared by 2G in this equation. And we can add up these two head losses in the system, in the pipelines, to get the value for the total head loss. So if you look at this equation, for example, if there are multiple pipelines that are connected in series or in parallel connections, so you have to add up the length for the pipeline for all the piping lengths that are in the system, right? And for the minor losses, you have to see that what is the value for the KL for each of the component for each of this kind of situation, and then you have to add up all the KL values to get the total value of the minor head loss, and then you can finally add up these two head losses to get the value for the total head loss. So let us see this one, that how we can actually calculate the value for the minor head loss due to these kind of equations. Now from this slide we will continue today. So the loss coefficient KL of various pipe components for turbulent flow for use in the relation HL, that is equal to KL V squared by 2G. So this one is a minor head loss, where V is the average velocity in the pipeline that contains the component. Okay, so for this velocity V, or this velocity V, we have to consider the average velocity. Now these are the two kinds of situations for the pipe inlet and the pipe exit system. Now for example, in there is some reservoir, and the fluid is coming from reservoir and going into the pipeline. Now in this kind of situation, the loss coefficient value will be equal to 0.80. Now there could be another situation in which the reservoir is connected with the pipeline but with the sharp edge. Okay, so you can see the difference. So in this case, the KL value will be 0.50. For the third case here, the reservoir is connected with the pipeline, but you see that the edge here, it is very well rounded. Okay, so there is some value, the ratio between the small r and the capital D, which is a diameter. If it is greater than 2, the value for the KL, it comes out to be 0.03. And for the other situation, slightly rounded edges, The value for this ratio is 0.1, so the loss coefficient, it will be equal to 0.12. So you have to see the situation, you have to compare the problem with this kind of situation, and then you can actually see that what should be the value for the KL. Now these six figures, these are relevant to the systems in which the fluid or the any kind of fluid, it is coming from the reservoir into the pipeline, or the fluid is going from pipeline into the reservoir. Now for the pipe exit system, the value for the loss coefficient, it will be equal to alpha. For the sharp edge systems, it could be also equal to alpha. For the rounded system, it can be equal to alpha. Now what is this alpha here? It is a kinetic energy correction factor, and its value is 2 for the fully developed laminar flow. So if the value for the laminar flow, if you get the value for the laminar flow, then you can use the value of alpha 2, and if you are getting the value for the turbulent flow, you can use the value for alpha 1.05 as a loss coefficient. Okay, now I repeat here, these six figures that we can see here, these are the situations in which the fluid is coming from the reservoir into the pipeline, or it is coming from pipeline and going into the reservoir. So these are the situations relevant with the reservoir. Now let us see what could be the other situations. Now there could be situation in which one pipeline is connected with the bigger pipeline, and there is sudden expansion going on in this kind of situation, right? So we can use this equation for the sudden expansion. KL, it will be equal to alpha multiplied by 1 minus small d square capital D square overall square. So this small d, it is the diameter of the pipeline, and the capital D, it is the diameter of the bigger pipeline. So you have to calculate this ratio here. You have to put the values, the alpha value you have to see if you are dealing with the laminar or the turbulent flow. And what we can see here, in most of the situations, in the practical situations in the industry, like in this kind of situation, the alpha value will be the turbulent flow, okay, because it will destroy the streamlines of the flow. So the value for the alpha, it will be 1.05, and this ratio you can calculate. So the value for the KL you can get from this equation for the sudden expansion situations when one pipeline is getting connected with the other pipeline. Now there could be another situation in which a bigger pipeline is connected with a smaller pipeline. So to get the value for the KL here, you have to rely on this chart for the sudden contraction system. So you will get the value for this ratio, small d square divided by capital D square, and then you will use the chart to get the value for the KL. Now there could be another situation in which there is a gradual expansion system, or there will be a gradual contraction systems. Now you have to see the value for the angles. So this was the angle here for the sudden expansion. It is 20 degree C, 20 degree, and the value for the for this ratio, small d divided by capital D, you have to see small d is diameter of the smaller pipeline, capital D is the diameter of the bigger pipeline. Okay, so you have to see these values here, and then you can get the relevant KL value. And for the sudden for the gradual contraction systems, similarly for the angle 30, 45 and 60 degree, you can have the fixed value for the KL that you can use from this figure. Now let us see if we are dealing with some kinds of bends and branches in the piping systems. So there could be like different kind of components that you can attach on the pipelines for connecting the pipelines, or to change the direction of the piping systems. Okay, so if you are dealing with the 90 degree smooth bend, so the value for the KL, it will be 0.3. For the flanged joints and threaded, if you are using the threaded joints, the value should be 0.9. Now what is the difference between the flanged and the threaded one? So you can see this figure here. For the threaded one, so if you are having the pipelines that are having threads on it, and you can connect this pipeline with another pipeline by using this kind of threaded components, then you can have this kind of KL value. And what is the flange here? If you are connecting the two pipelines that is having a flange on it, and you put like screws to connect these two pipelines, and there is a different value for the KL. So it depends on the type of connection you are developing between the two pipelines. Okay, so from here you can see the situation. If you are using the flanged joint system, then you can get the value for this KL 0.3. If you are using the threaded one, the value could be 0.3. Now if you are getting this one in the form of rounded, if you're using some kind of these bands that have the curve here, so the head loss would be less in this kind of situation compared to this one, right? This one is kind of very abrupt end, and there will be a sudden change in the direction of the fluid, so you will be getting a larger value for the KL, which is having the higher head loss in the system. Now for the same situation, if there are some meter bends in this band here, like the veins here, so the value for the KL, it will be 0.2, and there is another threaded elbow that you can use, so there will be a different value for the KL. So what we can see here, the systems or the bands or the branches that can cause a sudden drop in the pressure, or they can cause a higher value for the head loss, the value for the KL will be higher. Like in this situation, it will be having a maximum value for the KL, and this kind of bend, it can have a larger value for the delta P in the piping system. Now there could be like other components. You can see here, if you are using the 180 degree return bend, the value for the KL is 0.2 for the flanged systems, and the value for the KL is 1.5 for the threaded one. If you are using the T's, you can have the value for the KL. If you are using this kind of T, there is a different value for the KL. If there is a threaded union, so to connect these two pipelines, you are using some kind of union, the value for the KL, it is 0.08. So from these figures you can get the value for the KL. You have to just match the situation according to the problem in your question. Now you can also install some kinds of valves on the piping systems. You can use a globe valve, which can be fully open, so the value of KL is 10. You can have like angle valve, ball valve, swing check valve, and for each of the valve you can get the specific value for the KL. The gate valve, which is mostly used in the industries, so the value for the KL when it is fully opened, it is 0.2. When it is 25% open, it is 0.3, and if it is half closed, then the value for the KL is 2.1, and if it is 3 by 4 closed, the value for the KL will be very high, that is 17. Okay, so you can see by using the different valves, you can have different values of the KL, and if the valve is closed or near to the closed, you can have a very large value for the KL. Now let us see this situation here. This is, you can consider this one as a reservoir, and the fluid is coming from the reservoir into this pipeline, right? So this one is a situation of the contraction. So what actually happens in the, if you consider this one point 0, 1 and 2, and you can draw this one on the pressure profile or the pressure head equation that we saw in chapter number 5. So at this point 0, you can have the maximum value for the pressure head, that is P naught divided by rho g, and when the fluids enter within this pipeline, what would happen? At this point there will be a formation of some vena contracta, or the region in which there is a circular motion of the fluid. So at these 2 points, at the vena contracta, there will be no motion of the fluid, and all the fluid that is coming in this pipeline, it will be passing through a region which is having the minimum area, and at this point you can have the maximum value for the velocity. So what we see here, if we see the conversion of the pressure head into the velocity head, and then how this velocity head is again recovered into the pressure head, we can see this equation. Okay, so at the point 1, at the point 0, you can have the maximum value for the pressure head, but once the fluid enters into this pipeline, the pressure head is converted into this velocity head. You can see V1 divided by 2g, and the pressure head, it will be reduced. And when the fluid enters into the pipeline in a regular manner after this vena contracta region, what we see, some of the velocity head, it is recovered back into the pressure head. Now at this situation, at the point 2, there is some value for the pressure head. You can also have some value for the velocity head, and there is some loss coefficient. Some head loss will be in the system due to this contraction of the fluid within this pipeline. Okay, so that represents you the head loss in the system, KL V square by 2g, that is lost velocity head. Now let us solve this example here. The head loss and the pressure rise during gradual expansion. A 6 centimeter diameter horizontal water pipe expands gradually to a 9 centimeter diameter pipe as shown in the figure, and the walls of the expansion section are angled 10 degrees from the axis. The average velocity and pressure of the water before the expansion section are 7 meter per second and 150 kilopascal respectively. Determine the head loss in the expansion section and the pressure in the larger diameter pipeline. So we have to see that what is the head loss in this system and what is a pressure in the larger diameter pipeline. So first of all, how we can solve this problem here, we need to calculate what is the mass flow rate of the fluid within this pipeline. So the mass flow rate at the inlet, it will be equal to the mass flow rate at the outlet. So how you can calculate the mass flow rate, you can write in terms of density, velocity 1, cross-sectional area 1, and at the outlet you can have density, velocity 2, cross-sectional area 2. So the density is constant, so you can remove the density part and you can rearrange the equation in terms of velocity here. Okay, so when you rearrange the terms in terms of velocity here, the final equation that you get here, it is in the form of diameter at the inlet, diameter of the outlet, and the velocity at the inlet. So you will put the values for the outlet diameter, D1 it is the inlet diameter, D2 is the outlet diameter, and V1 it is the inlet velocity that is given here, 7 meter per second. Okay. Now the velocity V2 that you calculated for this problem, it is 3.11 meter per second that you will be using in this head loss equation. HL it is equal to KL V1 square divided by 2G. So the value for the velocity that you calculated here, it is 7 meter per second, and the other values you already know. It comes out to be 0.333 meter. Now the value for this KL, how you will get the value for the KL? This one is an equipment that we can see in the figure. So this one is a gradual expansion system, right? So what we can see here, we can go back here and we can see this figure here. So in the example we are dealing with the angle 10 degree, but this equation it is for the 20 degree. So we can for now we can use the same data that we are provided for the angle 20. So you will see that what is the ratio for the d by d, small d by the capital D, and then you can get the value for the KL. Now for this example, the value for the KL that is found here, that comes out to be 0.133 that we have used in the problem here. So the value for the KL 0.133, the velocity at the inlet, and then you can have the value for the G. So the head loss that you calculated for the given component, it comes out to be 0.333 meter. Now we have to calculate what is our pressure at the point 2, or what is the pressure within this section of this component. So what we can do here, we can use the Joule energy equation here, and then we have to simplify this equation. Z1 and Z2 can be cancelled out because there is a very less height difference between the inlet and the outlet. Then there is no pump in the system, there is no turbine in the system, so we can remove these two parts and we can rearrange the equation in this form. Now for the inlet pressure, we are provided in the question that comes out to be 150 kilopascal. Density we know, alpha value, what should be the value for alpha? It is we are dealing for, because whenever we are dealing with the small components or there is a sudden expansion going on, we get the turbulent flow, right? So whenever we are getting the turbulent flow, we will use the value for the alpha to be 1.06 or 1.05. Okay, you can use this value. For the inlet velocity, it is 7 meter per second. For the outlet velocity, we can calculate from the equation. V2 comes out to be 3.11 meter per second, and the value for the G is given. The head loss you have calculated this one, 0.333. So you can put the values in this equation, and the value for the pressure at point 2, it comes out to be 168 kilopascal, which is asked in the question. So I hope using this example, it can give you an idea that how you can calculate the head loss or the pressure drop caused by some of the small components within the piping systems, and how we can actually use a Joule energy equation to get the value for the pressure. Okay, so you can go through this example and let me know if you feel any difficulty. Thank you. There is one more thing in the today's lecture, that how we can compare the major and the minor head losses in terms of length equivalent. Okay, for example, we are dealing with some small component, and we want to see that how much the length of the pipeline would be required to cause the same head loss that can be caused by the small component. So what we can do here, we can compare the major head loss equation with the minor head loss equation that you can see here, the major head loss equation and the minor head loss equation, and the equation that you get here, it is in the form of length equivalent. What is meant by this equation, that what should be the length of a pipeline that is required to cause the same head loss in the system by using some component. Okay, so sometimes if you see some of the exercise problems, maybe you have to directly use this equation, or maybe you can also derive this equation using this one. Okay, so this is very simple from the derivation point of view, and you can also have an idea that what should be the value for the head loss for the small component, and what should be the length of the pipeline required to cause the same head loss. Okay, so maybe you can use this equation also. Thank you.